Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be talking about saturated solutions. This is more or less a fancy way of talking about exactly how much of a solute wants to dissolve in solution. And not too surprisingly, this is going to be a thermodynamically controlled process. Because as we've seen previously, the delta G of a transition or any type of reaction tells us how favorable it is. And it turns out if we know the enthalpy and entropy values for an individual set of processes, we can then use this to figure out the favorability. And so what we can do is use our Gibbs free energy of any sort of phase transition. For example, going from solid glucose to dissolved glucose, which has a positive enthalpy. It's endothermic, but entropy favored. We can use these values to figure out the Gibbs free energy for this reaction. And then what we can do is use our equilibrium constants that we've brought forward together previously. And if you remember, that's just going to be the concentration of products over reactants. In this case, since our reactants are a solid, only the products end up showing up in our equilibrium constant. And so this means we can determine our equilibrium concentration of glucose that has dissolved in water simply by knowing the temperature of the system and our Gibbs free energy. So this produces an ideal concentration for the glucose to achieve. And this is also known as a saturation concentration. So a solution is said to be saturated when its concentration equals this value. Because if you remember correctly, when the concentration equals our equilibrium constant, at this point, the delta G goes to zero. So the reaction isn't going to be moving forwards or backwards, which means that I have some level of solid and some level of dissolved species both present. And an easy way to try and identify whether or not a system is saturated is if I add more solid, does it does it keep dissolving? Alternatively, if I have any solid present and I've given it enough time, we can assume that the system is saturated. And as a natural tendency, systems want to be saturated. Now let's assume that our concentration is somewhere below this equilibrium level. Well, at this point, the system will be said to be undersaturated, and the Gibbs free energy will be negative, meaning that the reaction wants to progress. So my solid will keep dissolving as I add it. So generally, if I'm, say, adding sugar to tea, what we're going to end up finding is that it will keep dissolving and keep dissolving. And until you get to the point of a sweet tea or a Texas sweet tea, where you literally have sugar crystals, you're probably undersaturated. The moment you start seeing crystals form, you've probably reached saturated. Now, it turns out there's some clever tricks you can do to make a system super saturated. So this is a process at which you've managed to get more of the solute dissolved than it actually wants to. At this point, what we're going to do is start seeing crystals grow as whatever solute we have comes out of solution. So again, if you're dealing with a solid, you'll see crystals growing. If you're dealing with a saturated gas, it will start degassing. So think about something like a carbonated soda. You open the can, bubbles come out because it was super saturated. Now, a good way to illustrate these processes is going to be looking at rock candy. So one of the big things when you're looking at glucose and sucrose, which form the two classic forms of sugar, note that they have a positive enthalpy. This means that these reactions are endothermic. So if I add more temperature, I am going to end up increasing that saturation level. So that equilibrium constant will increase. So what you often do is you heat water to raise that solubility of the sugar, increasing the equilibrium constant, that saturation level. And then once the water is hot, you'll keep adding sugar until it reaches saturation. So until no more crystal sugar can be dissolved. So at this point, you can then either pour that pure water into a new dish or something along the like. Then what you do is you let the water slowly cool. Now, as the water cools, the solubility of the sugar is going to reduce back to the original room temp value because, again, lower temperatures will make it less soluble because of that endothermic nature. Now, because the I still have the same amount of sugar dissolved in the water, but my solubility has decreased. I now have more dissolved solute than saturation would allow. So the system is now super saturated. And so as it cools, sugar will slowly come out of solution. And if you do this slowly enough, you can make sure that it maintains a beautiful crystal structure. And that's the idea of rock candy, using a lot of our thermodynamic principles that we've already talked about for a cool visual. So next time, we're going to be applying a lot of these same ideas. Instead of looking at solids, we're going to try and figure out the saturation levels for dissolved gases. Until next time, take care.